The last HL topic is topic 18.3. And if you thought 18.2 was long, 18.3 is probably going to be twice as long. I am shooting this in one video. However, I do have like heading slides in between sections. So feel free to stop when you get to that section and move forward as needed because it's long. It used to be 4 sections and now it's 1. However, they all do interrelate. So I'm guessing that is why they put it into 1. pH curves, essentially titrations. And there's a lot of little bits of information you need to know to understand the big picture. In addition, I'm going to cover something that is not in topic 18.3, but it is in D.4. Therefore, you do need to know it because you need to know it for your options. And so I'm going to teach it now since you didn't get it last year. First, we need to understand buffers and what buffers are. They're actually really fascinating systems that I'll tell you about in just a second. So buffers act to reduce the impact of one thing on another. So like friends can be buffers for each other if there's fighting, so on and so forth. But in terms of acid-base solutions, a buffer is a solution that resists change in its pH when there's an addition of small amounts of an acid or a base into the system, and that way it tries to keep the pH at the optimal level. So our bodies are full of buffers. Like our blood needs to sit at roughly 7.2. And so by eating a lot of acidic foods, our system needs to be able to buffer that acid in order to not change the overall pH of our body. The ocean is a huge buffering system where it has the capability of absorbing carbon dioxide, and then that just turns it into carbonic acid, which is we saw in 8.5, how water can turn acidic with CO2. But that means there are things in the water, like calcium oxide, that is a base that will buffer any additional acid. However, any buffering system can be overloaded and overcome. And the reason buffers have to exist is if you have a system without a buffer. So we have water, right? And so we have water, pH is 7, 298 Kelvin. So let's say we add a strong acid, HCl. I could have thrown HNO3 or H2SO4 in here, which is part of acid deposition. We're only going to add 1 milliliter, so 1 centimeter cubed of a 1 molar solution. And it's going to drop that pH of 7 to a pH of 4. Vice versa, if we add 1 milliliter of a 1 mole solution of a base, it's going to increase it to a pH of 10. And that is a huge swing in its pH by adding 1 milliliter of a strong acid or base. And so there are buffering systems put into place to help protect living systems from any additional acid or base. So how do buffers work? Well, they are a mixture of 2 solutions for everything, because you have to be able to buffer for an acid or buffer for a base. Looking at acidic buffers first. So the job of an acidic buffer is to maintain a pH below 7. Whatever that happens to look like, it all depends. So what does the buffer solution look like? Well, you need a solution of a weak acid. So that's one solution. And then you need to mix it with a solution of the salt of a weak acid with a strong base. So this looks like, as an example, CH3COOH is a weak acid. And the salt, which means NaCH3COO, so we have that weak acid still present, and it is with the ion of a strong salt or base. So how this occurs, or how this works, I should say. So if you have CH3, and that's going to dissociate, and not fully, it just, because it's weak, into its ions. And then if you have the salt, and because salts are salts, they fully dissociate. So now we have a sodium ion and a CH3COO minus ion. All right, now what we want is we want to make sure we have a solution. So the goal is to have a solution with a high concentration of your conjugate acid-base pair. So what does that look like? So if CH3COOH is our weak acid, what is its conjugate? CH3COO minus. And we want to make sure, because if you look at the dissociation of CH3CO minus, you're like, well, it has its own conjugate base there, right? Well, because it's a weak, it doesn't dissociate much. That is why we guarantee by having a salt with full dissociation, we will have a high concentration of the conjugate base in addition to the conjugate acid. And so what these are called reservoirs. And so they're ready to react to any addition of H plus or OH minus added to the system. So what does that look like? So if we have our acidic buffer, and we are going to see how it responds. So if we're going to add some acid, an acid is going to react with a base. So that means that's our conjugate base, so CH3COO minus, that comes from the salt. And it's going to react with it. And it's going to produce the conjugate acid, CH3COOH. If we add our OH, or a base, that is going to react with our acid. Now, here's the beautiful thing about all this, right? So if we add an acid, it's going to react with our conjugate base, but it's just going to make more of the acid, the weak acid that's already in our solution. And then if we add a base, it's going to react with our weak acid that, hey, look, we just made some more, right? And it's going to make more of our conjugate base, which, oh my goodness, we need over here. And so it's this nice, cool little cycle that occurs. Now, because we are getting rid of this H and this OH ions, right? Those are not going to persist, and so therefore there is no pH change that occurs. Now the only problem with buffer systems is, let's just say we're going to constantly keep adding our H plus, right? Which means we're going to overload the system, and eventually we are going to use up all of our conjugate base. And that means you're going to overthrow the system to where the buffer doesn't work, and 1 milliliter extra of that acid could throw the whole system out of whack. Well, what about basic buffers? So basic buffers want to maintain a pH greater than that of 7. What does this look like? Well, it's just the opposite. You're going to have a weak base, like NH3, with a salt of that weak base from a strong acid, like NH4Cl, which that strong acid was HCl. If you couldn't tell. All right, so just like before, how is this solution set up? So if we have NH3, and it's with water, you make NH4 plus and hydroxide ions. The salt, because it is a salt, it fully dissociates into NH4 plus and Cl minus. So where's our reservoir? Our reservoir, we have our weak base, because remember it dissociates very little. We cannot hope for the conjugate acid. And we have the conjugate acid from the full dissociation of the salt, right? And so that has become our reservoir. So just like before, how does it respond to an acid or a base? So if we're going to add some acid, that is going to react with our base. So our NH3, our weak base, is going to react with that acid. And we're going to make us some NH4, which is the conjugate acid. Yay, right? And then we're going to add OH. That's going to react with our conjugate acid from the salt. And it's going to make our base. So just like we noticed before, when an H or OH reacts, it's going to remake either the base or the acid that was in the original buffer solution, right? And so just like before, because we get rid of that H and OH due to the buffering reactions, there is no change in our pH. Again, this can get overloaded, where if we constantly add one of them, so like a hydroxide, eventually we are going to run out of that NH4 plus, the acid, and that means the whole system is going to break down. So determining the pH of a buffer solution. So as I mentioned before, this is in medicine and drugs. So it's not directly in topic 18, but I will assess you on this in topic 18, so that when you get to it in medicine and drugs, potentially you will have recognized this calculation. So some assumptions we need to make is that the dissociation of a weak acid is small. Therefore, our initial acid concentration equals that of the concentration of our acid at equilibrium, as we discussed back in 18.2. The salt is going to fully dissociate. So the initial concentration of your salt is the same as the ion concentration at equilibrium. Now, if you go through and do this, you could actually figure out where some of your error occurs, just so that if you're looking at percent error, why would that happen? And it's called the common ion effect, and this is because it's due to all equilibrium reactions. So what happens is when you have the presence of a common ion, right? And so if your acid is going to dissociate, this acid is going to dissociate into an A minus, and your salt also dissociates into A minus, right? Well, that's going to suppress the presence of that A minus constantly being there is going to suppress the ionization of your weak acid or base and or reduce the solubility of your salts. And so that I just want you to be aware of as you potentially, if you calculate percent error and have to explain where that error is, it's due to the presence of a common ion. So what happens is if you have your acid, and that's going to dissociate into a hydrogen ion and its salt ion, and you have your salt, which is your base, and that dissociates into your metal and your anion. Well, mathematically, how we can go through and set this up, okay? So if we have our Ka equals H plus over A or times A minus, sorry, over HA, we can rearrange this to have H plus equals Ka times HA over A minus. Now remember, in our buffer, we are going to have a salt, and we're going to have, here we're using our weak acid, right? So this is an acidic buffer. So we know our HA, because it dissociates so small that the concentration of your HA at equilibrium is the same as your concentration of your HA initially. And because we know our salt fully dissociates, we can assume the anion concentration is going to be the same as what the salt originally was. So this allows us to rewrite the calculation as H plus equals Ka times the concentration of your acid over the concentration of the salt initially. So then we can take the logarithm of it all, and so pH equals pKa plus the log of your salt over your acid. Or you could take the pOH equals pKb of your salt over your base. Yet again, you guys need to have these memorized. I'm sorry. But where this comes in, right? So you can know your pKb for your weak base for a basic buffer, right? And you can go through and figure out what your concentrations are and figure out your pOH, but ultimately you want to know what the pH. And so once you know your pOH, you can go find your pOH or your pH based off pH plus pOH equals 14. And so every calculation I have given you is yet another route to find the opposite hydrogen or hydroxide ion concentration. Do not get overwhelmed with the volume of calculations. They're all just different routes depending on the solution you're given to solve for pH or pOH. So an example, and it's just a simple example, calculate the pH of a buffer solution that is at 298 Kelvin, prepared by mixing. So we're going to mix 25 centimeters cubed of a 0.10 mole per decimeter cubed ethanoic acid with 25 centimeters cubed of 0.10 mole per decimeter cubed of a salt. Your Ka is 1.8 times 10 to the negative 5 at 298 Kelvin. All right, so what we know is our concentrations, right? We already know our concentrations of our salts and our weak acid. So pretty simple. And we're using the same volume. Now, if these were different volumes, the different volumes then cause a different ratio, in which case you actually have to go through a different calculation. All right, so first, if we know our Ka to be that value, right? So we're working with a acid. So we know our pH equals pKa plus the log of the concentration of your salt over your acid. Well, I wasn't given anything except I know my Ka, so I can find my pKa, right? So my pKa equals the negative log of 1.8 times 10 to the negative 5. And that's going to be 4.74. So let's plug in our information. So pH equals 4.74 plus the log of a concentration 0.10 over concentration of 0.10. Yes! This equals 1. If you take the log of the same value or the log of 1, that's going to give you a 0. So that means your pH equals your pKa, which means it is 4.74. That is a beautifully easy calculation. Now, that only works when your salt and acid concentrations or your salt and base concentrations are the same. If they're not the same, you actually have to go through and calculate it. And you will see examples of those within your homework packet. So how do we make buffer solutions then? We just looked at how do we determine a buffer solution, what the composition of a buffer solution is. So ultimately, how would you go through and make one? First, you want to start with your weak acid or base, depending if you're making an acidic or basic buffer solution. And you want to make sure that you are picking an acid or a base appropriately based off the pH or pOH or pK or pKb values that you want, right? So if you're looking at making a buffer for the human blood, you want your pH or your pK or your pOH, pKb to be around 7.4, right? In the ocean, you're going to want it around like 6.0. So it all depends on the situation you're in. Then, so you're going to mix it with a solution of the salt with the conjugate acid or base, which would be the ideal situation. So that's probably not going to be given to you. Or you can make that salt solution by partially neutralizing your weak acid or base with the strong acid or base to make that salt. And that's the example I'm going to give you. All right. So say we're going to actually have to make one of these suckers, right? So CH3COOH. That is our weak acid, which means we need to mix it with a strong base. So that is going to be sodium hydroxide because we want to make that salt. And we need to be with a strong alkali, which means it needs to be lithium, sodium, potassium, or barium. And sodium's just easiest. So when you do this reaction, you're going to create NaCH3COO. Whoop, there's our salt. And water, because it's a neutralization reaction, in case you didn't know. All right. So what you want to do is you want to create a mole ratio. You need to have twice as much weak acid or base than you have strong. I cannot stress that enough. You need to have twice the amount of your weak acid or weak base as you have as your strong. So I'm showing your mole ratios. So initially, we have 2 times the amount of our weak acid than we do our strong base. That way, in order to cancel out that base, so to avoid the effect of having that strong base in our buffer solution, we need to make sure that we still have our weak acid. We don't really have water, right? So because we're making a buffer solution, we need to have equal amounts of our weak acid to the salt of that weak acid. We cannot have any of the strong remaining, so we need to zero that out. So you do not have a true buffer solution if your strong does not equal 0. And so you could actually be asked that question, set up this problem, you go through, you have your initial concentration, and says, what is your buffer solution? What's the pH of your buffer solution, right? If your pH does not equal your pKa, you do not have a true buffer solution. That means your strong base is partially there. When the concentrations of your acid equal the concentration of your salts, it is a perfect buffer solution. When they don't equal and you have some of the strong base, that means you do not have a perfect solution, and that can happen. So understand you need to have twice as much of your weak as your strong in order to make a 1-to-1 ratio of your weak to its salt. So things that can influence buffers. What if we dilute the buffer out? Well, because we're just diluting it, your Ka and Kb are not changed because they're controlled by temperature, right? Your ratio of your acid or base to its salt does not change because they're both in the same container, right? And so you're just diluting it out. Therefore, the pH of the full solution is not changed. What is affected is what's called the buffering capacity. And the buffering capacity is how much a buffer can withstand, so how much it can absorb of additional acids or bases. So as you dilute a solution out, you are diluting the effect of the buffering capacity, and therefore you're decreasing its ability to absorb additional acids and or bases. Temperature affects your Ka and Kb because they're equilibrium expressions. And so K is always affected by temperature. And that means as temperature changes, your pH changes. And it all depends if you're increasing or decreasing based off that situation, what's going to happen. So that is the end of buffers. And we're going to keep coming back to buffers. So if you need to take a break, please do so. We've got 3 more sections to get through. So salt hydrolysis first. So salt hydrolysis. Salt is a salt. Salt is the product of a neutralization reaction. Hydrolysis means to react with water. React with water, sorry. All right, so depending on the resulting salt, it may not actually create a neutral solution or a pH of 7. Go figure, right? Your life wasn't complicated enough. For no hydrolysis to occur, that is when you have a neutralization reaction between a strong acid and a strong base. That goes purely neutral. So an example of that is HCl plus NaOH. There are go-tos, right? They go through a neutralization reaction to create a salt and water. So when we do this, this solution actually has a pH of 7. It is truly neutral. Because these guys are strong, they're going to fully dissociate. And that means their products are weak conjugates. So weak conjugate acid and weak conjugate base. That means that they do not want to react to go back to their original parent acid or base. Therefore, they're just going to sit in solution and we're good to go. That's the easy one. Anion hydrolysis. So anion, which means you have a negatively charged species, is the conjugate base for the parent acid. So that means it's the ion from the parent acid when it dissociated. If you have a weak acid, you're going to have a strong conjugate base. And that means you're going to hydrolyze water. So an example, generic, you have your anion, and it's going to react with water to reform your original acid and a hydroxide ion. Oh, hydroxide ion. Look, anion, anion, negative, negative. That's how you remember it. So because you are creating a hydroxide, that means your pH is going to be greater than 7. Okay, so anion hydrolysis creates an anion, which is your hydroxide ion, which increases your pH. A real situation is if you have CH3, COO- in solution. And it's going to come from the dissociation of its salt, right? Because salts dissociate in water. It's whether or not those ions react with water in addition. So your salt dissociates, so that means you have CH3, COO-, and it's in water. Because it is a strong conjugate base, it really wants its hydrogen back. So it's going to reform its parent acid and release a hydroxide ion back into solution. Cation hydrolysis. So your M+ or your metal ion is the conjugate acid for the parent base. And so if you understand from anion hydrolysis, a weak base makes a strong conjugate acid, which means it's going to hydrolyze water. And so what this looks like is if you have M+, and that reacts with water, it's going to create MOH, so the original base, plus H+. Oh, look, here's our cation, cation, cation. Because we're releasing H+, that means our pH is going to be below 7. So an example, a real example of this, is NH4Cl. So this salt, which is made from NH3 and HCl, when that dissociates, right, we get NH4+. And that NH4+ is going to react with water to form NH4OH and H+. Therefore, having a cation hydrolysis, creating a cation as a product, which is your hydrogen ion, which is decreasing your pH below 7. Where we see this is going back to the Lewis acids. So with your metal ion, which is your cation, the outcome of its ability to hydrolyze water depends on its charge density. And charge density means that they are relatively small ions. but they have a large charge. So they create a really strong density. So like iron 3+ and aluminum 3+. And what happens is when they go through and make a complex ion with a ligand, like water, cyanide, or NH3, it's actually going to release hydrogen ions due to the formation of that complex ion. You don't really need to know the specifics of how that happens, as that is covered in topic 3, I believe, but I'm just reiterating it here. This table is just a nice summary of what happens during a neutralization reaction. And so go ahead if you want to write it down. It gives you some examples. It shows you what happens with the strengths. The one thing we did not cover was weaks. And weak acid, weak base, it all depends on the strength of their Ka and Kb's and how far they dissociate. And that will tell you the strength of their conjugates. And therefore, the ultimate, if they hydrolyze and then creates salt hydrolysis, you cannot generalize. So the first 3 are really the important ones you need to understand. We are now 2 out of 4, so we are now halfway through our lecture. I apologize. So titration curves, acid-base titrations. This is really the meat of it all. And this is, we have talked about neutralization reactions and how we actually go through and run those reactions is through a titration process. So this is essentially the summary of everything we have done. And we'll bring everything back together. So a titration is a technique for controlling the neutralization reactions quantitatively, because we can go drop by drop, milliliter by milliliter through a neutralization reaction and watch what happens during that process. That reaction is going to continue until it hits what's called the equivalence or stoichiometric point. So equivalence means equal, right? So that means that is the exact neutralization point. And so you're going to have a pure salt and water ratio. Now, based off salt hydrolysis, you will then be able to determine is the pH below, at, or above 7. See why we did all this? And we also call it the stoichiometric point because the stoichiometric point at this time is when they are at the correct mole ratios based off the reaction. So they can be referred to as either. We use titrations in the process of standardization in industry because we are able to calculate the exact concentration of one solution when we know the other. So when we're making, whether it's going to be makeup, food, it doesn't matter. It all goes through titrations to make sure we understand the concentrations and the acidity, basicity of all products that are put onto market. So this is a very common process. Titration curves, and that is what we're going to go through and decipher. These are plotted values that occur during the titration of change based off of their pH. So when we do a titration lab, a neutralization lab, our goal is to be able to create a titration curve to identify the point of equivalence and then therefore determine the pH of the resulting solution based off the theory of what it should be. Now the thing is, these are not linear curves. It's specifically called a pH curve because they are unique. The shape is very unique to a neutralization reaction. For the following examples that are going to be used, we're going to be using 0.1 moles per decimeter cubed solutions for both the acids and the bases. We're going to use an initial volume of 50 centimeters cubed of acid in the flask and 50 centimeters cubed of base in the burette because that's the maximum amount of volume that a burette can hold. And we're going to be using reactions where the acid and base are in a 1-to-1 ratio stoichiometrically. So we're not going to use sulfuric acid because then it messes up. And it just makes it a lot easier understanding the 1-to-1 ratio. And that means that the equivalence point is when you've used equal volumes of your acid and base. So that means we have 50 milliliters of something in a flask, and we're going to use 50 milliliters of everything in our burette, and that is going to create a point in which we know the equivalence is going to occur. All right, do your best to just sketch these graphs into your own notebook to the best of your ability. They don't have to be perfect because they are a general trend. So the first thing we're going to do is look at a strong acid, strong base reaction. So I'm sure at this point you've realized we're going to use hydrochloric acid and sodium hydroxide. And that creates sodium chloride and water. So that is what our resulting solution is going to look like at the equivalence point. Okay, so how do we go through and interpret the graph? So there's numbers, and you're going to have notes based off those numbers. So if you look, the initial concentration, the initial pH is very low. That signifies that you are working with a strong acid. Okay, whatever is in the flask below the burette is where you're going to start reading your pH values. Okay, so that means the acid is in the flask and we're adding base to the acid. The pH is going to gradually change. As you can see, it's not very sharp, it's very gradual until we hit the point of equivalence. And so the point of equivalence is this dotted line, because we said if we have 50 milliliters in our flask, at the point of equivalence, because we have a 1-to-1 ratio, we needed to have used 50 milliliters of our base. And that's going to give us our equivalence point. Now this is also known as the point of inflection. And how we read this, because there's a sharp jump, halfway up, that inflection is where we're going to find that equivalence point. And so you can read it on a graph you make yourself, which takes us to 3. We have that sharp jump, and that sharp jump, as you can kind of tell, goes from pH of 3 to pH of 11. It's a very large jump. So halfway between 3 and 11 gives you your equivalence point, right? After equivalence, or after your point of inflection, the curve flattens at a high pH. That's really bad, but that signifies that we have a strong base in the solution. And because we can go that halfway point up that point of inflection, our pH at equivalence is going to be 7. And the reason it's going to be 7 is because we're working with a strong acid and a strong base, which means they have weak conjugate acids and bases, so there's no salt hydrolysis. What if we have a weak acid and a strong base? So that is if we have CH3COOH and NaOH. And that's going to give us NaCH3COO plus H2O. So as you can see, the graph is a little bit different than if it was a strong and a strong. The initial pH for our acid is higher, so it has like a pH of 3, because we're working with a weak acid. So it's not going to dissociate as much, therefore the pH is going to be higher. The pH, which you would think by adding a strong base into a weak acid, you're going to have a sharp change relatively quickly. But remember, that point of equivalence cannot happen until you've used equal volumes of your acid and base. So your pH stays relatively constant until equivalence. And the reason being, and we'll talk about this in a little bit, but the reason being is we're creating a buffer, right? Because we're adding a strong base to a weak acid, creating a salt of that weak acid, in which case that's going to buffer the addition of your strong base to a certain point until the buffering capacity is pushed too far. We're going to have a sharp jump, but it's at a higher level. So the point of inflection isn't until about roughly a pH of 7, and it's much shorter than it was with a strong acid, strong base. After equivalence, the curve flattens out at a high pH, which, as we know, signifies a strong base. And the pH at equivalence is going to be greater than 7 because we're going to get anion hydrolysis. Because we're working with a weak base, that means it has a weak acid, it's going to have a strong conjugate base, which means it's going to hydrolyze water and release OH ions into the solution. So you actually it's not truly a neutral solution. It is going to be slightly basic. So I want to talk about this buffer region real quickly. So when we go through and we have what's called the half equivalence point, right? So that is when we used half the volume of base into our acid. And so we have 50 milliliters of acid, we have 25 milliliters of base. And so that's that 2-to-1 ratio we have talked about, right? To weak to strong, which is going to create a 1-to-1 ratio of our weak to our salt. So that is actually occurring in our flask and creating of that buffer. Now what's really cool is that buffer is being created pretty quickly, but when you hit that halfway point, that's a perfect buffer, right? And so if we go through and you go look at your pH equals pKa plus the log of your salt concentration over your acid concentration, because we've used 25 milliliters of base, that means we've made 25 milliliters of your salt, and that is in 25 milliliters of our acid. So that means our pH equals our pKa at what's called the half equivalence point. So you could graph this titration, right? And at half the volume, you are going to have your half equivalence point, in which case you can figure out what your pKa is for your weak acid without actually knowing what your weak acid is. So this is for an unknown weak acid, which is pretty cool. Now you could determine this calculation step by step by step as you're building up to that halfway point. But you are making a buffer, and we've already talked about how do you make that buffer. And that's where it applies here, is when we're going through these titrations, which is pretty cool. Third one is a strong acid into a weak base. So let's say we're working with HCl and ammonia, and that's going to create, ooh, that was bad, NH4Cl, which is a salt. All right. So your initial pH is low, right, because you have a strong acid. The pH stays relatively constant because, once again, you are making a buffer. And so you're going to have this buffer region. That's really bad. But you're going to have this buffer that is being created until you hit that equivalence point. And so once again, you can figure out your pKb from this situation because you have your weak base and the salt of the weak base. And so this is going to be for your pKb. Follow the same steps as last time at 25. You're going to know what the pH is, and then you can turn that into pOH and find your pKb, just working a different workaround. You're going to have a sharp jump, but it's lower down from 3 to 7, right? So that means halfway up there, you're going to have your equivalence point. After equivalence, you're going to have your curve flattens out at a much lower pH because you're working with a weak base. And then your pH at equivalence is going to be less than 7 because you're creating from a weak base a strong conjugate acid, which is going to hydrolyze with water, right? And it's going to release hydrogen ions. And that means you're going to create a smaller pH in your salt solution. So it's not a neutral solution, right? It's actually a slightly acidic solution. Lastly, weak acid, weak base. So we could take our CH3COOH with our NH3 and you create, it's really odd, but NH4CH3COO. It's funky, but it works, right? So you're going to have initially a high pH because you have a weak acid. The addition to the base causes the pH to rise relatively steadily. So there's no buffer because we have no strongs to make a salt. The pH change at equivalence, it's less sharp and less noticeable and actually very hard to determine. And then you're going to flatten out at a low pH, which means you're working with a weak base. That means the pH at equivalence, yep, you need to know your pKa's and your pKb's potentially to know who is stronger, to know what kind of conjugates you're going to have in order to potentially predict where the equivalence point happens. I've yet to see a problem like this. I have seen, can you identify the different titration curves? So just know like a squiggly line is your weaks. Lastly, we are almost done. We have 8 indicators. So what is an indicator? As we discussed prior in 8.3, it allows for a color signal to show that a pH change has occurred within your solution. And actually, indicators are made of weak acids or weak bases, depending on which one you're using. And so their associated and dissociated forms have different colors, and that is what we look at, right? So if we have an acid indicator, so H and then whatever indicator that might be, dissociates into H plus and the indicator itself. So here you'd have color A, and here you'd have color B. And then based on what's happening in your titration, it could shift from one to the other as this hydrogen ion concentration differs. So you could look at Le Chatelier's principles, right? So as you increase your hydrogen ion concentration, right? So if we're increasing that, we want to get rid of it. So we're going to make more of our HIN, which means we're going to color A. If we decrease the hydrogen ion concentration in our solution, which means we're becoming more basic, we're going to re-release that indicator back into solution, showing color B. So how does that change in color work? So if we are looking at an acidic indicator, so our Ka equals our hydrogen ion concentration times the indicator ion concentration over the acidic indicator. So at equilibrium, we're going to assume that our concentration of our indicator equals the concentration of the original acid. So that means if we know the Ka for that H plus for the indicator, that means if we know our pKa, we know our pH for the indicator. Okay? So what this is going to happen, and this is called the change or end point. So when this occurs, and as we add a small amount of an acid or a base, you're going to shift your equilibrium, and that's going to change the color. Different indicators have different pKa's, have different endpoints, but you pick your indicator based off what you think your change point is going to be based on the titration curves we just looked at. So indicators can be used to signal the equivalence point when the end point coincides with the equivalence point. So then how do you determine your proper indicator? First, you want to determine the combination of your acid bases that are reacting. Is it a strong acid, strong base, weak acid, strong base, strong acid, weak base, weak or weak? What does it look like? Because then you could deduce around the pH of the salt solution at equivalence. If it's at 7, above 7, or below 7. And then based off that, you choose an appropriate indicator based on their pKa or pKb values, which should match that of what you expect in your solution. And so here's an example. We have our curve, right? And so here we are reacting a weak acid with a strong base because we have a high starting point, right? And then we have a high ending point. So we know our pH is going to be greater than 7. So we picked an indicator, phenolphthalein, that has a pKa value of 9.50. Well, that's between the jump of 7 to 11 that occurs with the weak acid strong base. So that means it's within the range of what we expect the equivalence point to be. Therefore, phenolphthalein would help us predict when that neutralization occurs from your weak acid and strong base. And that, ladies and gentlemen, is the end of 18.3.